So let me connect my PN junction to, here is a metallic contact, remember. Now this is important, we are going to connect it to external world. So this is a metallic contact, and let us take a resistance and then a cell. So when the connections are made in such a manner where the positive side of the cell is connected to the P side and the negative side of the cell is connected to the N side, that means from our battery, from our cell, we are increasing the potential of this P side as compared to the N side. So that is known as forward bias. Forward biasing, it's called biasing. And this PN junction is called forward biased in this particular situation. So suppose the potential difference that we are imposing here through this external circuit is, let's say, VA. This is V applied. But applied doesn't mean this voltage. Applied means what is actually applied on the junction. What will happen? We are increasing the potential of this P side as compared to the N side. So if I take this N side as a reference side, zero potential, call it zero potential. Then before the cell was connected, this was at some potential, already at some potential, you know that. And now we are putting extra potential there. This VA is on top of that. That internal inbuilt potential difference is always there because of the electric field, because of these negative charges here, positive charges here. You have an electric field this way, and this electric field creates a potential difference. We have made all the calculations for that quadratic potential distribution. On top of that, you are raising the potential of this P side with as referred to this N side by this amount VA. And raising the potential means lowering the energy, because U is minus EV. We are talking of electrons, these energies. So these are all electron energies. So in this diagram, what is the effect? The effect is that P side energies are brought down. P side potential has gone up. So P side energies have gone down. So we have to shift this part. We have to shift this part down. That will be the effect. Okay. So let me draw a fresh diagram. So let me draw a fresh diagram of this band. Once again, before the cell was applied. Before the cell was applied, you had a constant Fermi energy, Fermi level for entire material. Then this is P side and this is N side. So here the valence band starts here. This was the valence band. The conduction band was here. And then here on this side, that N side, the conduction band starts here. So let's say the conduction band is here. These are the conduction band energies. All these quantum states correspond to conduction band. Okay, so this is EC here, this is EV here. Then this is EC here, and EV will be somewhere here. So the quantum states are here. Then you have this bending. Now what happens? All this energy had to come down. So our new picture will be that this EC has now shifted here. This EC has now shifted here. And I'm writing everything with respect to this N side. So I'm not changing the N side. Okay, it's all relative. The whole thing can be shifted up, shifted down. So it's all relative. So by applying a voltage which is presumably small as compared to this, you have your new EC comes here, your new EV comes here. This EV comes here. And the Fermi level also comes down. Here is the Fermi level, new Fermi level for P side. All right, so now you have two Fermi levels. For P side, you have a shifted lower Fermi level. And for this N side, you have different Fermi level. Here this is lower, this is higher. I told you that for one system you should have one Fermi level, but that was for equilibrium. Now we have disturbed that equilibrium by putting the cell, and constantly the cell will keep this potential difference fixed. So by doing this, by forcing this, we will be forcing some current to continuously flow, and therefore that static situation will not be there, and therefore you can have two Fermi levels on the two sides. So this is for N side and this is for P side. Now look at the majority carriers, diffusion of majority carriers. So start from here, N side. The majority carriers are electrons. So you have all those electrons. You have all those electrons here. These electrons are there. Large number of electrons. But as you go up, the number of electrons decreases, and that decrease is also this decrease is also exponential. Okay, like that. So earlier, which electrons were able to diffuse? Earlier, these electrons were able to diffuse. These electrons were able to diffuse, which were having energies more than this energy EC there. But now the EC is shifted here. Now you have quantum states which start from right from here. So now these electrons in this energy range, they can also diffuse to this side. these electrons can also diffuse to this side. Earlier only these were diffusing. Now these are diffusing, on top of this, these are also diffusing. So the diffusion will increase. The diffusion current will increase. And since it's an exponential reduction, the number keeps on getting smaller and smaller exponentially. If you come from top, the number increases. The density increases exponentially. So if you come here, if you come d distance down, only there is small change in the number of mesotic areas electrons. But the same energy if you come here or here or here or here, then it's exponential increase, and therefore this diffusion will increase many fold. And same will be the story for holes. You can work it out. If this level has gone down, so whatever holes were here in these quantum states, all those holes are now here. The holes now start here. So whatever the density was here just below this valence band, same is the case here. The distance from the Fermi level is same. And therefore it will go further deep. It will go further deep. So previously if you had one hole here in the picture, then now you will have many holes here, and all these things are shifted down. So you have extra holes which can diffuse, which will find quantum states here, and therefore the diffusion current, I diffusion, that increases. So in the absence of cell, you had I diffusion equal to I drift. If you call it I naught, then now the diffusion current is I naught multiplied by some exponential factor, which is in fact like this, EV by KT. Diffusion has increased. This V is this V, VA. What happens to the drift current? What happens to the minority carriers moving through this depletion layer under the effect of this electric field? Look at now the minority carriers. So on P side, the minority carriers are electrons. Okay, so fine. So let me draw on this diagram itself. So the minority carriers, originally your minority carriers start from here. This was the bottom of the conduction band. So these were the minority carriers. And under the electric field, they tried to move towards this n side, and successfully they could do that because you had quantum states all over. Now because of the shifting down, what will happen? These electrons now, they are not here. The quantum states are very much there. No, the quantum states are very much there, but the electrons start at the bottom of the conduction band, and that is here. So now those electrons are here. But doesn't matter. If the electric field pushes these electrons in this side, there's no problem. You have all over quantum states here, and therefore they can go in the same fashion. So for drift of minority carriers, this change in the potential barrier or energy barrier or shift in this band, etc., is not going to affect. Similar is the case for the minority carrier here on the inside. On the inside, the minority carriers are holes. So these are the holes here. If they want to come here, no problem whether EV is here or EV is here. These holes can always come to this side. So for small voltages, and generally the voltages on that is small, so it's not as large as this 1.12 EV or so. So generally, if this is small, you are only concerned in this area, and here the hole will come independently whether you are here or you are here. EV is here or EV is here. So the message is the drift current is not going to change significantly because of this forward biasing. So what is the net current? The net current is I diffusion and minus I drift, which is I naught times e power EV by KT and minus I naught. So it's like I naught and common e power EV over KT and then minus 1. So this equation is called ideal diode equation. There are several assumptions taken to derive this equation, and that is why it is called ideal diode equation. There are resistances involved. Depletion layer offers large resistance. Then the carrier concentrations at the edges of the depletion layer, there are some assumptions about those things involved. All those things are there. But it does give you essentially the relation between current in forward bias and the applied voltage, as long as the applied voltage is less than, rather much less than, that built-in potential that is there in the junction. So we will talk more about this equation and how in actual diodes currents go. That will be in next lecture. As ideal diode equation. Now before proceeding further, let me just give numerical values of this quantity for different values of applied voltage. This I naught is typically, this I naught, which is the diffusion current and same as drift current if there is no biasing, that is typically say few microamperes. So let's say 10 microamperes. And at room temperature, at T equal to let's say 300 K, this K into T is 0.026 EV. And if you apply say VA is equal to say 0.1 volt, that means E times VA will be 0.1 EV. So similarly for different applied volts, you will have a EV, same number, but this volts will become electron volts. And EV by KT. So EV by KT, for example, in this case, EV by KT will be just the 0.1 and then divided by 0.026, and the EV cancels out. So one can evaluate this number once the applied voltage is chosen, and then you can calculate this whole thing taking I naught say 10 microampere or so. And I have some data for you. If I take V here, applied voltage here, and E, this whole thing, let me take this whole thing, I naught e to the power EV by KT, and then minus 1. So at 0, this is 0. This is fine. At VA equal to 0, you have e to the power 0 equal to 1, 1 minus 1 is 0, so that is this. Then if you take 0.05 volt, if you apply this much, then it becomes 58 microamperes. And if you take 0.1, then it becomes 458. This is 46. This is not 58. This is 46. This is 46 microampere. This is 458 microampere. And if you take 0.2, applied voltage is 0.2. This is 21.9 milliamperes. And if you take 0.3, this number is 1.025 amperes. And if you take this as 0.7, then you have 4.9 into 10 power 6 ampere. So this gives you a kind of a feel that you cannot apply large voltages. You cannot apply large voltages here. The diode manufacturer will tell how much current it can sustain. If you send more current than that allowed limit, then this whole diode will be destroyed. So this actual voltage that you apply on the junction should be much smaller than this points. For silicon, this 0.7 is that typically, of course it will depend on temperature and many things, but a little bit on doping perhaps, but typically it is around 0.6, 0.7, and if you apply that much, you have huge impossible current, and that is understandable physically. If 0.7 electron volt is that barrier, energy barrier, and if you apply 0.7 volts, what you are doing? You are reducing that barrier to 0. There is no barrier. Then the entire majority carriers this side, entire majority carrier this side can just flow without any barrier. So that will be like a short circuit, So the actual voltage which is applied across the junction is much less than that, and in that limit, this equation is usable. Okay? Of course, the diode itself has some resistance to offer. So whatever you apply here may not go on the junction. This depletion layer has a very small number or negligible, we take it 0, no charge carriers. But in any case, that offers a very large resistance. The other regions outside depletion region where you have a lot many charge carriers, that offers less resistance, and in ideal case, no resistance in fact. So all those things are there. So this is about forward biasing. Okay, there is one more thing that I should tell, that if you have forward biasing, then what happens to the width of the depletion layer? We have derived that equation, that width was some square root of the 2 epsilon, and this volt appearing here, and then divided by E 1 over NA 1 over ND, something of this sort. We have derived that. So when you apply this forward bias, this V decreases. Remember, what is this V? This was that potential barrier. So now this V becomes V minus VA. The barrier height is decreased. If this is how the bands are, then this is the barrier height. This is the barrier height. This is P side, this is N side, and this is EC, and this is EV. And when you apply this forward bias, this EC reduces to some lower value, like that. And hence the barrier is decreased. So this was V, and this is that applied E times, or yeah, this is energy, so better to write E times VA. And now this is the barrier. So in place of V, it becomes V minus VA. So it is this. So that means the width of the depletion layer decreases. In forward biasing, the width of the depletion layer decreases. And that had some effect on the current also, because all that thermal generation of electron hole pairs is in the depletion layer. It's other places also, but that is an equilibrium situation. Here, because of the electric field, you have the drift and all those things, so some effect will be there. Now the next thing is reverse bias. What happens if I connect this circuit, but the polarity is opposite, so that higher potential is put here and lower potential is put here? Then what happens? You can very easily guess what will happen. Let me first remove some of this. If you connect it with opposite polarity, so that this side is at a higher potential, this side is at a lower potential, with respect to this side, what you are doing, you are reducing the potential of this side. If I take this as a reference, then by connecting this negative here, you are reducing the potential of this side, and therefore you are increasing the potential energy, or increasing the energy of all those quantum states which are there on this P side. So if you had this picture once again, so in forward bias, these quantum states, these energies are reduced, but in reverse bias, in this reverse bias, all these energies will go up. So now your EC will be like this. I am writing with reference to this N side, so that's why I am only changing this part like this. So it has shifted up. Okay. So when originally you had these quantum states, and you understand only few at this large energies, there are only few electrons left. All right, because of the Fermi distribution function and density of states, if you are far away from the Fermi energy, this number is very, very small, and only that part was able to diffuse, only small part was able to diffuse. And if you reverse bias, if you increase the barrier, then this diffusion will be further stopped, because now this will not go. Originally when your EC was here, this could have gone, but now that EC is here, this will not go. So the diffusion will decrease, and drastically, because as you go up, the population here, the availability of electrons here falls drastically. So diffusion current will increase, diffusion current will decrease drastically in this reverse bias. Already when there was no bias, VA was 0, then I diffusion equal to I drift, and that is of the order of few microamperes. Okay, so already that diffusion current was small, and then you increase the barrier, and it goes exponentially further down. So very quickly this diffusion current will decrease. Nevertheless, the story here, the majority carriers here are holes, these holes, like that. As you go away from this point, you have a smaller and smaller population. Then you have lifted everything up, and anything above this line is not allowed to go here. Your valence band states are here. So anything above this is not allowed to go here, and then you are lifting it up. So that diffusion of holes also decreases naturally. Minority carriers. Now look at the minority carriers. What happens? Where are the minority carriers? In N side, the minority carriers are holes. So these are the minority carriers. And similarly here in P side, the minority carriers are electrons. So here are those electrons. And you can see that minority carriers can easily go. Even in reverse bias, even if this EC has gone up here, no problem for these electrons. They can always go to this N side. And similarly for these holes, even if this EV has gone up, no problem for these holes. They will just go. Hence, in reverse bias, the drift is not affected by this increase in barrier. So you will have the drift current essentially same. Why essentially? Once again, look at this equation. For reverse bias, this will become V plus VA. Okay, you have increased that barrier, and therefore this width will be slightly increased, and therefore in more region, in a bigger region, slightly bigger region, you have those thermal generation of EH pairs. And if more EH pairs are generated in depletion layer, then the drift current will be slightly more. But that's insignificant, and for all practical purposes, you can take that in reverse bias. This I drift is almost the same, almost doesn't change. But the diffusion current goes down. Already it was this, but it goes down, and therefore this net current, which is now I drift and minus I diffusion. And this will be in opposite direction, in the direction of that drift. So your current is in this direction. So that's the expected direction from the cell also, N to P. This is your direction of I drift. So in this direction, and the magnitude will be smaller than I drift to start with. And then once I diffusion becomes totally negligible, you have applied some voltage, barrier has gone up, and then I diffusion has become almost 0. So it will stabilize at this I drift, which is I0. So on that diagram, IV diagram, on the reverse bias, start with 0, and then it gradually increases to this I0. And this is known as reverse saturation current. Okay, so it starts from 0, but very quickly it will attain that I0, and then it will remain I0 for large values of V, no matter how much you increase this barrier. There are some phenomena I will tell you cannot increase this barrier to very high values before disturbing this, but for reasonable values of V, which could be 2, 3, 4, 5, 6, 8, 10 volts, this side you cannot go even to 1 volt, but this side you can go to easily few volts, it remains at this I0. Okay, but the scales for this side and this side are very different. If you want to show it on the same plot, because this reverse saturation current, this current here, this I0 here is of the order of few microamperes. Whereas in forward bias, the currents could be easily in milliamperes, few tens of milliamperes. All right, so this is few tens of milliamperes, 10 milliampere, 20 milliampere, 30 milliampere, like that. So on the same scale, if you show, this line will be very easily hidden in the width of the axis, whatever axis you draw with your pen, pencil, or chalk. Okay, so generally what people do, they use different scales here. This scale is in microamperes, and this scale is in milliamperes. So you have to read it carefully. So this is how this IV characteristic takes place. Okay, so before talking to what happens if I apply very high reverse bias, I told you that there will be some problems if I apply very high reverse bias. But before going into that, let me show you this forward bias and reverse bias on a PN junction and see how the currents vary qualitatively on the table. So if you go to market and ask for a PN junction diode, this is what you are going to get. Okay, this is one variety. Commonly you get this type of PN junction, and you can see it's a black covering. Your all semiconductor is inside that, and at this right end here, this end, you can see a silver band here. I hope you are able to see that silver band, this band here, and that is to tell that this is the N type side of this PN junction. So this will be your P side where you do not have that silver band, and the other side where you have the silver band, that will be the N side. So that is how I know about it. Now to give a voltage on this, I will be using this battery. And this battery, it's a 9-volt battery. So this 9-volt I'll be connecting to this heater coil. So this is a heater coil, and I'll be connecting this to this heater. All this 9-volt I will give on this heater coil. This is known as potential divider. So what I'm making is a potential divider. So I connect this end of this is the positive end of the battery, to one end of this coil, and then the other end of the battery, this is the negative end, this will essentially go here. So I'll just put this thing here, and I'll connect it later, but I'll connect it here so that this whole 9-volt drops on this. And then I connect I take another wire and connect this, there's a positive end of this potential divider, and I am connecting it here to the diode. So one side I have already given to the diode, and then the other side I'm taking it through this galvanometer. This is a galvanometer, and I'm connecting this galvanometer to the other side of the diode. So now what is happening? And this end of the galvanometer I'll be touching here. So if I connect this battery negative to this point, this is 9-volt here, and then if I touch it here, what is the circuit on the diode? This is now my potential source. I can make it 0.1 volt or 0.2 volt just by sliding. So suppose this is that potential source here, and then from the positive side I am connecting it to the P side of this diode. This is the P side without silver band. So from the positive of this potential I am connecting it to the P side, and then the N side is going to the galvanometer, and then back from the galvanometer back to this lower potential side. So this is a forward bias situation. Okay, and the potential that I am giving to this diode, of course the resistances etc. are there, will be just this much, whatever potential is on this. So let's start the experiment. So first I connect this cell here. So now there is a potential drop of 9 volt or whatever is the battery voltage here, and then I can use this much of potential difference to see what happens to that. You focus on the galvanometer. See, there is a current. Okay, see, there is a current. As I increase this, you have a current. So this is that forward biasing. And if I do the reverse biasing, let me invert the polarity of this main battery. So I put the positive side here and the negative side here. Now what is happening? This negative side, this is the lower potential, and this will be the higher potential. So the lower potential is connected to P side of this PN junction, and the higher potential side is connected to the N side. So it is in reverse bias. And now I again give potential to this, and you look at this galvanometer. You don't see any current. I'm increasing the voltage. See, I'm increasing the voltage. I'm increasing the voltage. I'm increasing the voltage. And there is no current anywhere. Microamperes. You cannot see in this instrument. There is a reverse current, but that is in microamperes that you cannot see from here. So whatever voltage you apply, you do not have a current in the reverse bias. Whereas in forward bias, you saw that if you apply some sufficient voltage, then you have this current. So the diode offers low resistance in forward bias, and diode offers very high resistance in reverse bias. So now let me talk of what happens if I have very large reverse bias voltage. Large reverse bias voltage also means wide depletion layer, this equation. Okay, if you apply a large reverse bias voltage, you are increasing the barrier, and therefore you are widening the depletion layer. So the electrons or the holes which are drifting because of the electric field, a whole electron pair is generated in this depletion layer, and that electron is, this is the drift, this is the direction of electric field, and therefore the electrons will go in this direction and holes will go in opposite direction. So if this electron is going in this electric field, it is gaining energy. Okay, the electron is going in this electric field, it is accelerating, it's gaining kinetic energy, and therefore, and the depletion region is wide, therefore it has sufficient time also. So it can gain so much of energy in this depletion region because of the effect of this electric field that it can knock off an electron from the bond, and this electron can produce a new electron hole pair. Okay, so the electron which is drifting in this direction, they can create, these electrons can create, these charge carriers can create new whole electron pairs, and when this electron is accelerated, it can produce yet another whole electron pair here, and this can produce another electron hole pair here. And of course the electrons are all accelerated towards right in this figure, and holes are all accelerated towards left in this figure. So if that happens, it's called avalanche. If that happens, if you apply so much of electric field and the depletion region becomes so much wide that the electrons can create new whole electron pairs, and those can also create new electron hole pairs, etc., then you will have a large current in this reverse bias condition also. Okay, you will have electrons are going this direction, so the current is going in this direction. You will have a large I drift. This is known as breakdown. This is one mechanism. There are other mechanisms also, but the fact is that if you have reached that breakdown, then it can suddenly, the current can suddenly increase many fold. So this will be the complete IV characteristic. This is one branch or one part, forward bias, this is reverse bias, and this is breakdown, and this whole thing makes this IV characteristics. And when you use this as a circuit element, then you have to understand all these things. Okay, so that is for today. injection. And then for these minority carriers, you have a concentration gradient. Now I'm talking of the mechanism of current once you have a forward bias. So for these electrons, for example, here, you have large concentration here because of this diffusion, because of this injection. And as you go away from the depletion region, you have a very less number of minority carriers here. So you have a concentration gradient once again, and therefore there will be a diffusion of these carriers. These are now minority carriers which are diffusing from right to left, from the edge of the depletion layer to this contact here, And if this width is sizable, then in the process, these electrons can combine with the holes because there are so many holes sitting here. So the electron, when combines with the hole, the charge stability or the charge equilibrium or steady state condition, that will be disturbed. Okay, because the electron has come from outside and it has gone. That is all right. But the hole has also gone together with it. And if a hole has gone, that means negative charge has appeared. So somewhere that negative charge is to be withdrawn. So this cell which has to maintain the potential difference. And if charges change here, then that potential difference will change. And so this cell will do the required job to maintain the potential difference. That's the job of the cell. All the chemistry inside the cell is for that, to maintain a potential difference. And so if this electron combines with a hole, and if this hole goes out, negative charge appears, so one electron has to be withdrawn. So one electron is withdrawn at this contact, and then the electron goes this way, the current goes this way. So similar is the story on this side also. The holes are having large concentration here at the edge of the depletion layer, and on the other side towards the contact, they have to diffuse. And during diffusion, they can combine with this electron, and one electron can go. And if one electron goes from there, once again, the negative charge goes, and therefore this circuit will supply an electron through this contact here to compensate that. So that is how the current goes. And all these things are in a controlled fashion. You control that biasing voltage, and then you control all varieties of the phenomena here and resulting current also. Okay. So on the forward bias side, you had your IV characteristics exponentially going like this. Whereas on the reverse side, you have almost zero current, almost negligible current. If you change the scale here, microamperes, this is milliamperes, then perhaps you are able to see on this plot. So this is what we discussed. Now, symbols for this diode. You had seen the diode yesterday. I showed you the actual diode that you obtain in the market if you go. Okay, this circuit we had shown. So that diode is in circuits. All the time we do not draw these rectangles. The symbol for that is you draw a triangle, this kind of triangle, an isosceles triangle, and put a line at this vertex, and then these are two lines here. So this is the symbol for diode. So whenever in the circuit we have to show a diode, we will be putting this. So if I redraw this circuit, it will look like this. I have a cell, I have a resistance, and then I have a diode, and like this. And in the symbol, this side here, this base side, this is known as, this represents P side. And this vertex here and a line here, this represents N side. So when I draw my circuit in this fashion, what I'm telling that the P side is connected to the positive of the battery, the N side is connected to the negative of the battery. So this is how the symbols are made. Okay, then for several applications, we can approximate our diode characteristic in different fashion. And one application that I'll be dealing today, that is known as rectification. I'll just tell what it is. Rectification means you have an AC source, AC potential source, AC voltage, and from that you make a DC potential, DC source, DC voltage. From AC voltage you make a DC voltage. Very, very useful thing, necessary thing, because all the power that we obtain in our households is AC power, right? Alternating current power. And all the gadgets that we use, most of them, laptop or camera or phone, mobile phones, they need DC current, they need DC power, they need DC voltages to operate. And that's why you always have a charger together with your equipment. And the charger goes in that socket, and the other end goes into your equipment, and in between there is something which actually converts this AC from the mains to DC and then supplies that DC to your equipment. So that making DC voltage from AC voltage is known as rectification, and using this diode, the basic element of rectification you can obtain. But for that I'll take a model, or I'll model this diode, this IV characteristics. In the forward biased condition, you see that you have large current, at least after some few tenth of a volt, you have large current. So a slight change in voltage gives large change in I. You can say that the resistance here is very, very small. Whereas in reverse, you apply so much of voltage and you don't get current, significant current, so the resistance is very, very high. And I'll approximate this as in forward bias, we will assume that resistance is negligible. Resistance offered by the diode is negligible, whereas in reverse bias, resistance offered is very, very high. Okay, so if I draw a IV characteristics corresponding to this situation, that will be something like this. Okay, it will just it is zero here, and then suddenly it goes like this. Okay, so this is I and this is V. So for the reverse bias, there's no current. Resistance offered is infinity. It's open circuit. It's like open circuit. Whereas once it is forward biased, the diode doesn't offer any resistance, and the current goes very high. Now, why this peculiar drastic approximation? Is it anywhere close to the reality? Yes, it is, because for forward bias, the circuit has some resistance. The circuit has some resistance. So if this resistance is small as compared to that circuit resistance, this approximation is not bad. And similarly, in reverse bias, if this resistance offered by this is very large as compared to the circuit resistance, outside circuit resistance, it's not that bad. And whatever is happening, we are shifting this large change towards origin. But this is only 0.1, 0.2, 0.3, like that volts. And therefore, the voltages in the circuit in the actual application is much more than that. Then that shifting is also not very bad. So depending on what application you are doing, that models are to be developed to understand that mechanism, that physics. Okay. So let me talk more about this rectification, how this rectification is done or can be done, or at least the basic unit can be developed using this diode. So suppose you have an AC source. AC source means your potential V, potential difference V, the voltage is applied, it's some constant times cos or sine omega t, like this. And AC sources are shown by the symbol. So you have two ends, and the voltage which appears here, the potential difference which appears here, is this V. And then let us say you have put this resistance here. Let us say this is just a resistance. What will happen? You know what will happen? You will have a current, and that current will be some V by R, V naught by R cos omega t. That is it. And if I ask what is the voltage appearing on this resistor, so that will be same as the voltage appearing here. If the connecting wire do not have resistances, then whatever voltage is here, potential is here, that same potential is here. Whatever potential is here, the same potential is here. So if I say that this is 0, if I call this as 0, then this potential here will be just V naught cos omega t, and that means it will change sign. So the current will go in one direction, and then current will go in other direction, and so on. The current will change sign with the frequency guided by this omega. This is angular frequency. So whatever is that frequency, our mains comes at 50 hertz. So if I put my mains here, then this will be 50 hertz cycling. That is what happens when I put my filament bulb or a heater in that socket, 5 ampere socket. So through that heater coil, the current keeps changing the direction, and voltage across that will be again changing the directions. Now what happens if I put a diode in between? Okay, so let me put a diode in between. Let me put just a PN junction here, just a PN junction here. And let me call this point as A and this point as B. So, and this is 0, this is all 0. So what is VA? Potential at A, VA. That will be just the potential difference between the source. So let this be V naught cos omega t, and the question is, what is VB? So if there is a current I, in this direction, then this VB will be equal to I times R. Right? Ohm's law between this point and this point. If the current is I, this VB minus 0 will be just I into R. So what is I? And for that, we have to use the property of this diode. So if I show this voltage on this graph, time this side and VA this side, so it's just V naught cos omega t, so it is like this. So I should go to the same height and all those things, which I will not be able to do, like this. Okay, it's not a good drawing, but you bear with me, but let me improve, try to improve. This should go to the same height, so let it be up to here. Then again it is up to here, and so on. All right. Now with the same scale, if I draw VB as a function of time, till here, till this time, what is happening? VA is positive. So this has a positive voltage. This is a positive voltage. Your P side is connected to a positive voltage, and then this will be connected to this 0 side. So higher potential here and lower potential here. This is forward biased. And if this is forward biased, and in our model or in our approximation, we take that forward biased resistance to be negligible, then it is just the old circuit. It's just a short circuit. So it's just this portion is shorted. So you just have a wire and like this. And so your VB will be same as VA, and you will have this part. The same story. I should copy paste here, but I cannot do that. So just like that. After that, during this period, what happens? During this period, this time, VA is negative. So this is at 0, but this is at negative. So that means this is the higher potential side, and this is the lower potential side. So P is connected to the lower potential side, N is connected to the higher potential side, and this is reverse bias. And if it is reverse bias, and if it offers very large resistance, if I call that resistance as infinity, no current flows through this. No current flows through this. So in that case, this I is 0, and therefore the potential here is same as potential here. V is equal to potential difference is I times R. I is 0. So the potential here is 0. Potential here is 0. Potential here is 0. So VB will be 0. So this in this period, this VB remains 0. And once again, this potential becomes positive. So in this period, you have a current like this, or voltage like this, and the current will be here. Then in this period, you have a reverse bias, and the voltage is 0. There's no current. So remove this arrow. But in this period, once again, it is forward bias, and you have current. So put that arrow back. Okay. So if I do not put the diode, the current goes in this direction and also in this direction. So it oscillates. The direction of current changes with the frequency given by that omega. But once you put the diode, this current going from this point to this point, this side, this direction is not there. Current only goes in one direction. So current only goes in one direction, and the other part is just 0. So the potential difference which appears across this is in fact a DC voltage. It does not change direction. It's a direct current source. This has become a direct current source. Okay, so you can obtain this DC voltage source from AC voltage source just by putting one PN junction in the circuit. So let me do some experiment here to give you some kind of
and holes. The p-n junction is a structure that, under certain conditions, can spatially separate electrons and holes. By forward biasing the device, which consists in applying a higher voltage in the P than in the N material, the current flows through the structure, causing the electrons and holes to meet in the same region of the space. This process is known as carrier injection. When there are many electrons and holes in the same region of space, more than those corresponding to their equilibrium values, carrier recombination is enhanced and energy structure filling the empty state in the bond. In this process, the electron releases energy as heat or as electromagnetic radiation. To make recombination more effective, the p-n junction is replaced by a heterostructure. An active zone composed by several thin layers of materials having different band gap width is embedded in it. The band gap width in some layers is lower than in the surroundings. Electrons tend to occupy the lower energy levels of